All right, let's look at this problem that deals with partial fractions as well. So once again, just like with the last example, we want to start off with factoring the denominator. So this is a difference of cubes. The difference of cubes will always factor into the cube root of the thing in front of them, the minus or plus sign, minus or plus the thing, the cube root of the thing behind it. So the cube root of x cubed is x, the cube root of 1 is 1, and then the other factor, we always are going to use these two things that you just came up with. So this first piece is going to be this one squared. You multiply these two together, change the sign. So this is a negative 1 times x. So if I change the sign, I'll get a positive x. And then the last piece will always be that piece squared. So negative 1 squared is positive 1. And there is the factored form of the denominator. Now, when you do this, you will always get a quadratic that cannot factor. And so because that is a prime quadratic, it's not a line times a line. Like the other example we saw was like x plus 2 squared. And so we did an a over x plus 2 and a b over x plus 2 squared, right? Well, we can't do that here because this is a quadratic because it's x squared, but it can be written as a line times a line. This one can't. The one that we're dealing with can't. So what we have to do is the fact that this is x to the first and this is ax to the 0, it's a constant. The degree is 1 lower. The same thing's going to happen here. This is a quadratic that can't be factored. 1 degree lower would be a line. So instead of writing just b, I'm going to do bx plus c, right? Think a line mx plus b. We're just doing whatever number comes next in the alphabet plus whatever number comes next in the alphabet. We're just doing the mx plus b with these particular letters. So there is the form of the decomposition. All right, as with all of this, we always multiply by the denominator of the left-hand side, and that's going to clear out the fraction completely on the left side, but only take off one piece on the right side in each of these fractions. So we're going to get a times x squared plus x plus 1, and then the line bx plus c times the x minus 1. All right, just like before, we're going to distribute and expand. So I'm going to get ax squared plus ax plus a from that first piece. And then here I'm foiling, so I'm doing bx squared minus bx, and then a cx minus c when I distribute all that through. All right, now I'm going to combine everything that has an x squared, set that equal to 8. Everything that has an x, set that equal to 4. And then everything that is not got an x or an x squared is equal to 9, a constant. So I have an a plus b is equal to 8. I have an a minus b plus c is equal to 4. And then I have an a minus c is equal to 9. All right, for this I would definitely use the Desmos calculator. I'm going to make a new matrix. This time because we have a, b, and c to solve for, there's 3 equations, so I'm going to make a 3 rows by 4 columns. Okay, it's always going to be one more column than rows, but the rows is like how many equations there are, and we have 3. All right, there's 1a, 1b, no c's equal to 8, so that's going to be 1, 1, 0, 8. All right, then we have 1, negative 1, 1, 4. All right, and then finally the last one is 1, negative 1, 9. I should say 1, 0, negative 1, 9. So there's my matrix A, and then I want to go down to RREF, matrix A. There is my solution. So A is 7, B is 1, C is negative 2. So 7, 1, and negative 2. All right, and now I know what the form of the integral is going to look like. So the thing over x minus 1, A, was 7. The thing over x squared plus x plus 1, bx plus c, was 1 and negative 2. So there's what the integram looks like. So I'm going to split this into 2 integrals. I'm going to do the integral of the 7 over the x minus 1. Right, that's just going to be 7 log absolute value of x minus 1. And then I'm going to split it up into this one, the integral of x minus 2 over x squared plus x. Now this one is almost, if I did like a u substitution, I've got a quadratic on the bottom and a line up top. That would be really nice if it worked out to be the derivative of x squared plus x plus 1 is in the numerator. But you'll see if I let u be x squared plus x plus 1, du is 2x plus 1 dx. And I have an x minus 2. So if I divide away the 2, or if I multiply this by half, you can think of that. I'd have 1 half du. I would have 1 half du is x plus 1 half dx. And I don't have that, but I can kind of force it. I can force it to happen, meaning what do I need to make this be plus a half? Well, I need to add 5 halves. And I can add 5 halves as long as I also subtract 5 halves. All right, and then I can break, again, this part of the integral into these two integrals. Okay, no, don't forget you also have this over here that's part of the integration. So here, this is the integral of u on the denominator, and then x plus 1 half dx is 1 half du. I know how to do that. That one's easy as well. That's a 1 half natural log absolute value of u, and again, u is all that stuff. So I could say this is 1 half natural log absolute value of x squared plus x plus 1. So there's another piece to the integral. This is coming from that integral. All right, and then finally we're left with this one. And this one, unfortunately, is the worst one of them all. All right, so the first thing I would do is just take the 5 halves out of the integrand and have this be just 1 over x squared plus x dx, okay? Now this is not a perfect square, all right? X squared plus x plus 1. So what we're going to do is make it be. We're going to complete the square. And to do that, we have to come up with what does this constant need to be for this to be a perfect square. So the way that we do it is we take half of the number in front of x, and we square it. And that's what we're going to add and subtract. All right, notice we added it here, we subtracted it here. Now this part becomes x plus 1 half squared. All right, fold it out, you'll get this. And then this part becomes 3/4. So there is what we have now. This is dx. And why would we do this? Well, the answer is because now it looks like the squared variable plus something squared. It looks like the things from the table that we've seen before. So we have something squared plus something else squared. This looks like an inverse tangent. I recall, if I'm going to use the tables, I need to manipulate it to make sure that it's something of the form that the table applies. So I'm making it look like what the table has. All right, if you want to do u equals x plus a half to kind of make sure that it looks exactly like it, that's fine. But just make sure that you understand how to use it, how to manipulate it to make it look like this. Okay, so this is negative 5 halves, obviously going to be on the outside. This is just, if there's a constant out here, then there needs to be a constant out there. That's just using how we have to use the table. All right, but the thing being squared, the variable, is this. So that's what's going to be in place of that x. And the thing that is the squared number is the square root of 3/4. And the square root of 3/4 I can write as the square root of 3 over 2. So 1 over a, this is a. 1 over that is going to be 1 over the square root of 3 over 2. Inverse tangent of x. Again, x is x plus a half divided by a. And a is the square root of 3 over 2 plus c. All right. I'd be okay if you got that. It's ugly. But this can be simplified. So I got a negative 5 halves on the outside. 1 over a fraction, you just flip the fraction. So that's 2 over the square root of 3. Inverse tangent. And the same thing here. I can write this as 2 times x plus a half over the square root of 3. And then the 2 in here will cancel. This will be a minus 5 over the square root of 3. Inverse tangent of, if I distribute through, I'll have a 2x plus 1 over the square root of 3 plus c. There's the final piece. Okay, that's just the final piece. That's not out on its own. Remember, that's part of the problem. All right, and there finally is our completed integral after all of that work. Okay, so that's a beast of a problem. And that's going to happen when you have a quadratic factor like that. In the denominator that can't be factored, those are going to be the tough ones. Those are the ones that are going to have to break apart and use an inverse trig function from the table. But again, you got to make them look like that. You got to get them into the right form.